Bonsoir, merci bien. I would like to give my lecture in French, but unfortunately I've never been able to find the time to learn it. I think I fully followed most of the lectures today and also this very kind introduction. I really appreciate the honor of receiving these awards and to be with you today, one of my first, probably the first business trip in 1.5 years. And we are here celebrating almost with no face masks. I think this is a really good reason to celebrate. Thank you so much. So for this presentation, I selected a title which allowed me to talk essentially about anything I wanted, because this title could be like a summary of the activity of the past 30 years in my laboratories. So I will probably focus mostly on the synthesis part, and I will show you an example of applications which involves also assembly. I hope that's all right. Before starting, I wanted humbly to find the resemblance between myself and the people who give the name to this binational award, Miguel Catalan and Paul Sabatier. Very briefly, Miguel Catalan is best known for his works on spectroscopy. And as you will see, spectroscopy is one of the major tools that we use, adapted to the new field of nanoscience. Paul Sabatier, among other things, has worked quite a lot on catalysis using metals. And even though this will not be included in the talk today, we have also been working at some point on using metals as catalysts in different ways. And so I'm really honored to bear this award with these two names who have contributed so much. Now, if Sabatier would have been working in the past maybe 10 or 20 years, he would probably have gone to doing catalysis with much smaller metals. And this is probably a useless introduction in this auditorium. You are all familiar with the concept of nanoscience and why working with very small pieces of materials is important. And so the main point is that when you reduce the particle size, you increase a lot the percentage of atoms which are located on the surface rather than in the interior of the material. And not only by doing that, you increase the number or you increase the available surface area, but you also increase the influence of surface properties in the overall properties of your material. In the case of some metals, not all of them, but there are actually many metals, this also influences quite a lot the way that light interacts with matter. Again, one of the objectives of the work of Miguel Catalan. And so, to introduce it very briefly, when you have a bulk metal with free electrons, there will be a specific wavelength of light that will couple with the oscillations of charges inside of the metal, and this is what we call a bulk plasmon. If you have a very thin metal film, a few nanometers across, then these charge density waves will not fit inside of the metal, so they will localize at the interface between the metal and the dielectric. And if you have very tiny particles, which are nanometer dimensions in all three directions, then in the simplest case, the electric field, the oscillating electric field of the electromagnetic radiation will couple with the oscillation of dipoles with free charges in the metal particle. And so this phenomenon is what we call localized surface plasmon resonance, and it is responsible for the very bright colors of colloidal dispersions of tiny metallic pieces. So colloidal silver looks bright yellow, colloidal gold looks bright red or wine red. But this is actually what you see when the particles of silver or gold are made of very tiny spheres. And I will discuss this a bit more in the lecture later on. And of course, the appearance of these very intense colors is coupled to these very intense extinction bands in the visible. And so depending on the dielectric properties of the metal, you will have a plasmon resonance at a different wavelength, and so you will have a different color in the dispersion of the particles. Another very important effect of this interaction of light with matter is that when light is coming in this direction, polarized in the perpendicular direction, you will also excite very high electric fields at the surface of the metal, which actually also decay very quickly away from the surface. And these very high electric fields are also very relevant to properties of these materials because they can largely influence the spectroscopy of molecules that are located next to the surface. And so by exploiting these properties of nanoscale metals, you can find also plenty of applications. And I'm just showing you a couple of them that we'll not have time to discuss in this lecture, but we have been working intensively during the past 10 or 12 years on the use of surface-enhanced Raman scattering, which is based on the amplification of the Raman scattering of molecules located next to metal particles. When they feel the high electric field at the surface, the polarizability of these molecules is also affected, and so you can enhance the intensity of the Raman scattering in many orders of magnitude. So then Raman scattering becomes not only highly selective, but also extremely sensitive. So you can use this technique to identify even the presence of single molecules in a system. And so we have been working largely on this topic. One example is shown here where we used arrays of gold nanorods to amplify the Raman scattering signal of molecules that bacteria use to talk to each other. So these are biomarkers which are specific of the communication between bacteria. So by using these islands where we have the nanoparticles, we can really obtain the signal of these biomarkers so that we can understand how bacteria behave. Another example that was also actually mentioned this morning after your Roche's lecture is the use of light to selectively heat metallic nanoparticles so that the electric field, so that the energy injected by the light into the nanoparticles is converted into phonons which vibrate and then release part of this energy in the form of heat. And this can be applied to selectively kill, for example, cancer cells in so-called photothermal therapy. So these are some of the reasons why we want to understand how these systems work, how these systems can be fabricated, how they can be fabricated in a way that their properties are optimized. And so I mentioned already that when you have very tiny particles, you can get these very sharp absorption bands when the oscillating electric field couples with the oscillation of the dipoles. When you increase the particle size in spheres, what you see is actually that this band is shifting toward higher wavelengths, red shifting, and it also becomes broader, and this is because the coupling efficiency is hindered when the particles become closer to the wavelength of light. However, one of the most exciting properties of these materials is that particle size is not really the most relevant effect, or causes not the most relevant effects. It's actually anisotropy, which can be used as the handle to very finely tune the wavelength at which there is coupling between light and matter. And so by elongating nanorods, for example, you can finely tune the position of this band from the visible all the way into the near infrared, even into the mid-infrared. And so by doing that, you can really select the material that you want to apply for any of the applications that you have in mind where a specific wavelength of light will be of interest. And so it's actually quite interesting to work and understand the chemistry behind the fabrication of materials with such an exquisite control of particle size and morphology. So let me guide you through the synthesis of gold nanorods. And this was probably, so the initial works on this direction were actually date back to the early 1990s. And I could mention the work of Sumi and Wang as probably the basic pioneers. And then Catherine Murphy was the first one to actually highlighting that if you can separate nucleation and growth, then you are in a much better position to obtain high-quality nanorods. And so the idea is you first use a very strong reducing agent like sodium borohydride to quickly reduce gold chloride into gold crystals of very small sizes. And then these crystals are stable for a while. If you leave them for a long time, they will probably ripen and become bigger, which can be used at an advantage, as I will show in a minute. But typically, you use them very quickly after making them. And then what you do is adding more gold chloride in the presence of cationic surfactant, and also in the presence of a weak reducing agent like ascorbic acid, so that now the reduction of gold ions into gold atoms does not create new nuclei. They only grow on the existing seeds. And by selecting the right amount of surfactant and probably other additives, you can very selectively grow elongated particles, so nanorods. And by selecting the conditions and mainly the concentrations of all the reactants that you see here, you can tune the elongation of these particles. Now, another important point is we are using here this cationic surfactant, CTAB, cetyl trimethyl ammonium bromide, where you have a charged ammonium head group, which will likely bind to the surface of the metal and complex with the metal atoms on the surface. And then it has a long hydrophobic chain. So since these particles are to be stabilized in water, we typically add enough surfactant that there is formation of something that probably looks like a bilayer, so that you have also charged head groups on the outside, and you obtain an electric double layer that will stabilize the particles in water. So this is quite important. It will be relevant to most of my synthesis part. Now, CTAB has a very rich phase behavior, which has been studied largely by French scientists for a long time, but also by other people, where you can find not only spherical micelles, but also cylindrical micelles, lamellar phases. You can even obtain these worm-like micelles, which can also be affected by co-surfactants. So this is quite interesting, and it probably answers some of the questions why these particles grow elongated. And this has been already used by Cathy Murphy in her initial works, talking about a sort of templating effect by the double layer of surfactant, where the atoms would have to be reduced at the tips, and then more surfactant molecules would come and protect the growing particles. This was a bit tricky to understand because the cylindrical micelles typically form at surfactant concentrations which are much higher than the ones we use in the synthesis. And so there were other theories. Our work together with Paul Mulvaney in Melbourne was actually related to the distribution of the surface potential depending on the elongation and the curvature of the particles. And so the idea was, if after growing spherical particles they become slightly elongated because of symmetry breaking, then the most curved parts of the particles will have a potential that decays much faster, so that the micelles with gold ions will be easier to be reaching these highly curved parts and increase the elongation of the particles. And all of this, I think, still makes sense. But one of the crucial contributions came from Philippe Guyot-Sionest in Chicago, where he actually discovered that the two typical types of seeds that were used to make nanorods, either using sodium citrate or using cetyl trimethylammonium bromide in the initial reduction with borohydride, do not have the same crystalline structure. So they are, all of them, they are FCC. but the CTAB reduced particles or protected particles are single crystalline, while the ones which are reduced in the presence of citrate actually are pentatwinned. And this is what I signal here with these lines. If I would blow it up, you would see twin planes that create defects in these particles. And so the type of nanorods that you obtain from single crystal seeds and from pentatwin seeds look similar, but they are not the same. So the ones you grow from the single crystalline seeds are also single crystalline, most of them. The ones which grow from the pentatwin seeds actually form either bipyramids or pentatwin nanorods. And this is quite interesting, and it also opens up plenty of questions and parameters to be investigated. And so recently, together with my former PhD student, currently group leader Marek Jelczak, we wrote this piece about the challenges to really understand how metal crystals grow and what is the actual growth mechanism. And we suggested that apart from learning about the crystallinity of the seeds and controlling the crystallinity of the seeds, it's also very important to have at hand simulation tools that allow us to really model the growth of these crystals, not only to know their properties, but to actually see how this combination of thermodynamics and kinetics can lead to these anisotropic shapes. But also single particle imaging, either in liquids or on TEM grids. This is also a crucial tool that we have been using for a long time that can still bring many of the answers. And here I wanted to show you an example of the use of single particle characterization to understand these nanoparticle systems. So these are gold decahedra that we made already 15 years ago. Time flies. And so this was quite interesting. The morphology is very similar to the very tiny seeds I showed you a minute ago, but they can grow very large if you find the right conditions for that. So at that time, we did this by using dimethylformamide as both the solvent and the reducing agent. And so one of my students was presenting this work at a conference, and then a scientist who was established in Toulouse, Martin Heitsch, came to him and said, can I have a few of those particles? Because I have never seen so well-defined decahedra in large sizes. And they are very tricky because they are made of 5 tetrahedra of FCC crystal. And so if you put together 5 tetrahedra, the angles don't match the 360 that you need to close the decahedron. And so what Martin did was first to do high-resolution TEM, and then he was measuring with electron holography the stress in each of the single crystals that form the five single crystals becoming together. And with this, it's actually easier to understand how the thermodynamics works to stabilize this type of particles. Another interesting application of electron microscopy for characterization of these systems came in our collaboration with Christian Colliex and Mathieu Kosiak in LPS, initially Orsay, I think it is now Saclay. And they were the first to apply electron energy loss spectroscopy to image surface plasmon resonances with electron microscopy. And this has been a really successful collaboration that is still existing today, already since 2007, and I'm very happy with my collaboration with Mathieu. Now, coming back to the nanorods, another example of characterization. For a long time, it has been claimed that for single crystal nanorods, the lateral facets are a combination of 110 and 100 facets of the LCC crystal. Now, again, my student Enrique Carbó Argibay was working with assemblies of gold nanorods which were standing perpendicular to the TEM grid. And so what here looks like spheres are actually the cross-sections of standing nanorods. And this you can see by tilting the grid, you can see that they become like deformed because now you're watching a tilted nanorod. And so if you find the right orientation between the electron beam and the standing nanorod, you may be able to do high resolution of the cross-section. And then by doing electron diffraction or FFT, inverse Fourier transform, you can actually see that the lines connecting the lateral facets do not correspond to 1,0,0,1,1,0. They do correspond to actually higher index facets that were not identified before. And coincidentally, my friend Paul Mulvaney was doing exactly the same thing at his lab in Melbourne, together with people at a neighboring university. And this actually has been corroborated now by a few other scientists. And again, by our collaboration with Sarah Bals in Antwerp, where they can do high resolution, I would say atomic resolution electron tomography. So they are able not only to see projections with atomic resolution, but actually to turn the nanoparticles and then reconstruct in 3D the position of every atom and identify the facets and the tips. Okay, so this is one of the reconstructions that show the 8 lateral facets, all very similar dimensions, all 5 to 0 index. Now, for the pentatwin nanoparticles, this has been a difficult subject, and it was difficult mainly because making seeds that are all pentatwin is very tricky. And so we have been working on this, making the decahedra, the nanorods, the bipyramids. The yields until very recently were always rather low. And this means that if you see earlier pictures of pentatwin nanorods like this, you should be suspicious. So in our 2004 paper, we show pictures like this, but with the complete image that also shows a population of spheres. And this is because initially you have a mixture of single crystals and pentatwin seeds. All right, so recently, and actually inspired by the work of Stéphane Parola in Lyon, again, Marek Zielczak together with Ana Sánchez Iglesias, they started exploring the ripening of the pentatwin seeds. And so again, reducing with sodium borohydride, now in the presence of a mixture of citric acid and CTAC, they were obtaining what we would call very low quality seeds. But then by incubating at 80 degrees for a couple of hours, even 1.5 hours, they were seeing a gradual increase in the particle size, but also a large increase in the proportion of particles that have the 5 twins. And these are again images coming from our colleagues in Antwerp. And they were able to do actually statistical analysis of the population of pentatwin seeds and corroborate that this increase in particle size that also is reflected in a more intense plasmon resonance leads to many more pentatwin particles that then you can use as seeds. And this is again against previous works because now these seeds are about 6 nanometers in diameter, which always have been thought to be too large to act as seeds for the growth of nanorods. However, if we now use these ripened seeds, we are able to obtain pentatwin rods that look always like this. Almost no spheres present in the system, and also really tight tunability in the aspect ratio, so you can see the gradual shift of the plasmon resonance. This would be another resonance goes across the particles, not really affected by the particle elongation. And also in the longer ones, you see another band which corresponds to tetrapolar resonances. Now, again, what about the surfactant bilayer? And this is so please stop me if I'm speaking too long. I probably become too excited about this. So the bilayer, this was something that was, as I said in the beginning, explained as one of the basically only possibilities to stabilize these particles in water. And actually El Sayed, who was also one of the pioneers of these systems, applied FTIR and TGA to analyze the surfactant layer on the nanorods. And this was in agreement with the presence of a bilayer, but of course this comes in bulk measurements. We also did some work, again, together with French colleagues. Our MIST friend, Olivier Spala, who was the expert in small angle scattering. So one of my students, Sergio Gómez Graña, spent some time with Olivier and with Fabien to start at the CEA. And they were studying in combination of small angle X-ray and small angle neutron scattering to separate the contributions from the metal particles and from the organic corona. And by analyzing this data, they identified a thickness, an average thickness of the surfactant layer of 3.2 nanometers, which was, say, a bit shorter than what is found for bilayers on flat surfaces. And this was interpreted as a higher degree of interpenetration between the hydrophobic layers in these bilayer systems, or by the possibility that we would have incomplete bilayers. Another piece of evidence behind the formation or the attachment of the surfactant on surfaces comes from theoretical analysis, density functional theory, calculations by Nuria López at the CIC in Tarragona. And for this analysis, we actually also used the presence of these complexes between silver ions and CTAB, which were also proposed by Olivier and his student Fabien Hubert. And by doing that, you can actually understand that the stabilization of the 520 facets at the sides makes sense from a theoretical point of view. From a thermodynamic point of view, I have to acknowledge that kinetics is not yet involved in these calculations and should also come into play. And so by following the different energies for different facets in the different steps during the growth of the nanorods, we can see that actually 520 get more and more stabilized when you are depositing gold and silver ions. I didn't mention them, but they are necessary to make the single crystal nanorods in the presence of bromide. And bromide is, again, a very crucial ingredient in the system. I don't have time to talk about this, but it's very important, bromide, because the binding energy is in between chloride and iodide. And so bromide can actually bind and get released from the surface. So it allows the deposition of the atoms while still protecting the surface. So by exploiting all these concepts and using all these parameters, we are now able to make almost routinely dispersions of nanorods that look like this. And we can make them in a way that we can control the aspect ratio and tune the plasmon resonance, as I showed you earlier. However, if you compare any of these spectra with the calculations for one single nanorod with the average dimension of what you see here, you actually find that these spectra are actually still broadened. And this is because in a colloidal dispersion, it's almost impossible from simultaneous growth to obtain completely monodispersed system, so all the particles being identical. And this is why you get an average contribution to the optical signal. Now, can we improve that? And another very talented student, Guillermo González Rubio, together with a former postdoc, Andrés Guerrero Martínez, they have been working on the interaction of ultra-fast lasers on metal nanoparticles. And so this was when Guillermo was doing PhD with both of us. And they were so exploring the effect of femtosecond lasers on nanorods through all these mechanisms that, again, injects energy into the metal. Part of the energy is released to the solvent. Part of the energy can be used to reshape and so sort of melt the metal slowly and reshape into an equilibrium geometry. And so these are actually Monte Carlo simulations of what happens when you're injecting femtosecond pulses into a metal particle with enough energy that each pulse is actually promoting a small reshaping of the nanorod. When the wavelength of the light is not matching anymore the aspect ratio of the particle, this reshaping will stop. And as a result, you can go from dispersions like this with a spectrum like the red one into spectra like the blue one, which is as narrow as the theoretical prediction. However, this only works if you have the right concentration of surfactant. If you are using a much higher concentration of surfactant, then you obtain a bimodal distribution because this effect is not so well controlled. And so our argument to explain this is that close to the critical micellar concentration, the bilayer is incomplete in agreement with the measurements by Olivier, while at higher concentrations it may become more complete. So in this case, part of the energy that you're injecting with your laser into the particles can be released to the solvent quickly enough, while here it gets accumulated and protected inside the particles, so the reshaping will be less controlled. So anyway, so this is one of the ways to make very highly monodispersed nanocrystals. Another way to improve monodispersity is the use of co-surfactants. And this is again the work of Guillermo, where he, well, following work from the lab of Chris Murray at the University of Pennsylvania, Guillermo proposed that by using endecanol, you can use it already in the initial stages and go from very tiny seeds, which are roughly spherical, as I showed you, into elongated seeds, so very tiny nanorods that then can be used to grow larger nanorods with predefined dimensions. And so by starting with nanorods like this, very thin ones, less than 10 nanometers in diameter, you can actually grow now basically anything you like, with extremely well-controlled dimensions, with very narrow plasmon resonances. Now, playing with co-surfactants again opens up plenty of opportunities. And again, Guillermo, with another postdoc, Jesus Mosquera, decided to exploit and explore the possibility of introducing chirality in metal particles. We are not the first ones, but we are the first ones to propose it in this way. So the idea is that the same as in organic molecules, you can have chirality when you have chiral centers, so non-superimposable mirror images. In metal particles, typically you have high symmetry, so no chirality. If we were able to make helices, then the interaction of circularly polarized light to one hand or the other hand would be different with each of these helices. And so we actually found this paper in one of my favorite journals for a long time, where they showed that, again, playing with CTAB, but now introducing chiral co-surfactants like binol, you can obtain in solution elongated micelles that contain chirality. So they are like not perfect helices, helical micelles. And so by selecting different co-surfactants, we held the hypothesis that if these micelles can wrap the nanorods in a sort of helical manner, they might template the growth of grooves of gold that will keep the helical morphology. And of course this works, otherwise I wouldn't be showing you this in this lecture. And so we did again theoretical modeling by molecular dynamics. We found that there is a hint that the different enantiomers will lead to different organization of the micelles around the metal cylinders. And then we decided to run the experiments, and starting from nanorods like this, we were growing in the presence of bynamine and CTAC. And as you can see, we obtain grooves. The helicity is not extremely clear here, but quite interesting. If we now increase the amount of gold that is reduced on the same number of nanorods, we obtain similar grown rods where the center is still exactly the initial solid nanorod, and now the grooves grow even longer and even longer. And this is quite interesting because this really confirms that the micelles are templating the growth of gold on the surface. Now, how can we confirm that there is chirality here? We can do that by, well, first looking at the particles in more detail. I don't have time to explain all the analysis. Here, I think you can see more clearly that there is helicity, so there is a tilt in the orientation of the grooves. But I think more interesting, you can find very intense optical activity. And not only that, by tuning the dimensions of these grooves, you can tune the position of the circular dichroism peaks. And you can also correlate it with theoretical simulations of the interaction of light with models that look like our particles. And also, if you use the different enantiomers of the co-surfactant, you can obtain mirror optical activity bands, circular dichroism, which confirms again the templating effect. And now, if I have 5 more minutes, 5, no more, I will tell you very briefly about one other possibility of introducing chirality and actually giving it a practical application. And this is now related not to growing chiral particles, but to assembling particles into chiral arrays. And so this has been done in the literature in many different ways, mostly using DNA or DNA origami, which is very interesting, and you can obtain model systems, but it's not very practical. What we proposed a few years ago was that by working with amyloid fibers, we would at the same time have the perfect templates to organize gold nanoparticles into chiral arrays, helical arrays, and we might find a way to help diagnosing very important diseases, as all the neurodegenerative diseases listed here. And of course, this is a wild proposal. And so what we did was to look in the literature, see that some of these fibers really may have double helical structure, and the dimensions may actually fit with the dimensions, with the sizes of our gold nanorods. And so from previous work that we have done already 10 years ago, we expected that these type of assemblies would give also well-defined optical activity. And so we started working with a model protein, alpha-synuclein, that our colleague Aichiber Kortajarena could express from bacteria in our labs. And then by incubating the monomeric protein, we could obtain the amyloid fibers. And then what we did was incubating the fibers with gold nanorods and then measure circular dichroism. And as you can see here, over time, we could see an increase in the intensity of these CD bands that show that something is going on that now promotes chiral interaction between circular polarized light and the assemblies of the gold nanorods. If you look in the electron microscope, you actually see that over time, there are like longer and longer arrays of nanorods that somehow seem to follow the direction of these fibers. And then our colleagues again in Antwerp were able to do cryo-electron tomography and show that indeed there is a sort of double helical organization of the nanorods that explains the optical activity that we see. And it can also explain it because we can also do now modeling that shows that similar arrays would give also optical activity similar to what we see experimentally. And now the proof that it could be applied at some point was done in collaboration with another colleague, Joaquín Castilla, at our sister institute, CIC biomaGUNE. So Joaquín is an expert in this type of proteins and has access to the local biobank. So he gathered 4 brains from dead people, 2 of them who died from different diseases, 2 of them who died from Parkinson's, which is closely related to alpha-synuclein. And so by extracting the substantia nigra where these fibers are known to accumulate and doing some homogenization and then incubation with the nanorods, to our astonishment, we found that the 2 control brains led to almost no changes in the linear optical absorption, to sort of noise level circular dichroism, while the Parkinson's brains led to broadening and redshift of the linear plasmon absorption and much better defined circular dichroism. So it's probably too early to say this is a conclusive evidence that we could diagnose Parkinson's, but we are definitely interested in continuing the research in this direction and perhaps even giving a new tool for those who try to understand these diseases. And with this, I finish. I think the conclusions, I leave them up to you because I ran a bit too late. I would like to thank you for your attention, all my dear French colleagues and friends. I didn't mention all of them, collaborators in Spain and in other countries, and the funding agencies. Thank you very much.